Okay, hi everyone. Thanks for being flexible today. Welcome, by the way, as well. So you have a quiz on Monday for what we haven't been tested on yet. So that should be like all of your electromagnetic spectrum stuff, and then like these quantum numbers and whatnot that we've been talking about the past couple of days. And then quiz next week, spring break the week after, and then your next exam comes up kind of shortly after that, but you got time before the next exam, so don't worry about that one yet. You should also be getting midterm grades by Friday or so next week, so just be on the lookout for that. I'm just finishing those up the next 2 days. Okay, any questions for me about anything class-wise? Okay, any questions that we want to see today? I'm assuming we want to do quantum numbers.
You know, the one with like, if you have a certain amount of kinetic energy, like the joules that would be used, so you give a maximum amount of kinetic energy. However, there's like one homework question. Dealing with kinetic energy.
Yeah. Do you remember what homework question it was, or like what?
I think it was the second class homework, and like the first homework question.
Okay, I can pull up that homework real quick, just to kind of see what you're talking about. Was it due on, what's the date today? It was due the 23rd. Okay. Oh, this upcoming, yep. One second. Sorry, I have all of them loaded, so, okay, I think it's this one. The periodic trends one. Yeah, ionization energy. So I have like, using the periodic table, arrange the following elements in order of increasing ionization energy. The homework for that one. Okay.
Sorry.
No, you're good. Make sure I have the right one. A neon atom emits a light at many wavelengths, two of which are the ones given, and they have the same final state. What is the energy difference between them? Yeah, sure. Okay. So we have a wavelength of 621.7 nanometers and 703.2 nanometers. And we're saying that in an atom, right, let's say that when we go from n equals 3 to n equals 1, we get, oops. N equals 3 to n equals 1, we get one wavelength. And as we go from n equals 2 to n equals 1, we get another wavelength, right? One's red, one's blue. If we were comparing n equals 3 to to n equals 1, right? That transition compared to n equals 2 to n equals 1, which one has a greater energy difference? 3 to 1 or 2 to 1? Mm-hmm. 3 to 1 has a greater energy. I guess energy of 3 to 1 is greater than the energy of 2 to 1. Sorry. Right, so there's a greater energy difference between 3 to 1 than 2 to 1. So if we have a greater energy difference, does that mean we have a longer or shorter wavelength? Right, big energy equals what to wavelength? We have a shorter wavelength. Okay, so which one? 662 or 621.7 or 703.2 would be the 3 to 1 transition.
Oh, wait, 620.
621, this would be the 3 to 1, and this would be the 2 to 1 transition, right? Because we have a shorter wavelength, that means that they're closer together, which means we have a higher energy. Okay, so just looking at that, this would be 621, and this one would be 703. So the question here is saying, what is the energy difference in joules between the excited state and the final state of each of these transitions? Okay, so we want to know what the energy of those of those photons are, of those wavelengths are. So how do we solve for the energy of these? What's that equation we use? We have energy is equal to h times frequency. And we have the speed of light is equal to lambda times frequency. So what can we do to those two equations? We can solve for frequency. And so we can plug this into here. So we can get energy is equal to hc over lambda. So can we solve for the energy of each of these directly? Yes, we can. Right, so for the energy of the 621, we have 6.626 times 10 to the negative 34. What is our C constant? Perfect. That is given to you. You don't need to memorize this. But that's the speed of light. Right, it's all based off of the speed of light. And then we can plug in our what was it, 0.7? I plug in our nanometers. Right, nano is times 10 to the negative 9. So I got 320 times 10 to the negative 19 joules. That would be for the 621 one. Would we expect our energy for the 703 to be bigger or less than 3.20? It should be less than, right? It should be less than because, right, the energy difference is smaller. So there should be lower energy for our second wavelength. So for the energy of the 703, it's going to be the same setup. So we get 2.8. We should get 2.8. Why is that doing that? Sorry. So we should get 2.83 times 10 to the negative 19 joules for this one. So that is less than the energy from the 621 nanometers. Okay, so that's how you would solve that first part of the homework question. Does that make sense that way? So then it says B, if the transition between the two higher energy states could be observed, what would be the frequency in the light? Okay, so instead of asking about wavelength energy, we're now talking about frequency and frequency and energy, excuse me. So now we're saying instead of going from 3 to 1 or 2 to 1, now we're just going between 3 and 2, right? We want to go from 3 to 2. What is the difference there? So how would we find the difference in energy that way? Yep, you could just subtract the 2 that we just solved for. So we have 3.20 times 10 to the negative 19 minus 2.83 times 10 to the negative 19. So I got 3.7 times 10 to the negative 20th joules. And then how would we solve for frequency here?
Divided by 8.
Yep. Yeah, perfect, right? So we're going to use just this equation. The energy is equal to h times frequency. We can just use that directly. So we'll take 3.7 times 10 to the negative 20th joules equal to 6.626 times 10 to the negative 34 times frequency. So we get 5.58 times 10 to the 13th hertz for that one. So if we were to solve for the wavelength here is 5.37 times 10 to the negative 8th. So this is now larger, right, than nanometer. Your visible light sticks to the nanometer range. So now this is outside of the nanometer range, which is why they're saying if this were to be observed, right, we can't physically see that, but it could be detected that way, right? And so that's a good way to check to make sure that you're solving that properly as well. Does that make sense how to do that question? Yeah. Any other questions on that homework? Any other questions that you want to see today? How do we feel about what we talked about in class today? Okay.
How do we solve for how many electrons are sticking to something?
Yeah, that's a great question. So when we talk about, right, these all come down to quantum numbers. Right, so a quantum number technically has 4 numbers associated with it. So let's just break down our rules. Right, we have N, L, M sub L, and M sub S as the 4 different quantum numbers. Okay, so if we have N, what are our rules for N? What can N be? Close. Any number but 0. So any integer greater than 0. So that is 1, 2, 3, 4. Cool. So for L, what are our rules for L? Perfect. This is going to be n minus 1. So as an example, if n is equal to 4, what can L be equal to? Can L be 0 this time? Yes. Yep. So you have 3, 2, 1, 0. All right. So the other thing to note is that, right, if n is equal to 4, that's telling you that you have 4 options for L. 3, 2, 1, or 0. If you have n equal to 2, you have 2 options for L. 1 or 0, right? Those are your options there. That's just a good way to remember it as well. Okay, and then if you have M sub L, what are those rules there?
Can you go from like the negative version of that number,
Mhm.
to the positive version?
Perfect. Perfect, right? So you can have negative L to L, and this is including 0. So if L is equal to 3, M sub L can be -3, -2, -1, 0, 1, 2, 3. Okay, and then for n sub s, what are our options? Good, so you can have +1/2 or -1/2, right? This is telling you an upspin or a downspin, and this is just telling you what the electron can be. Right, no 2 electrons can have the same quantum number. So at the end of the day, each orbital only talks about 2 electrons. You can only fit 2 electrons in each orbital, and that's because they can either have a +1/2 or a -1/2, right? It's not -1 +1 0, right? It's up or down, upspin or downspin. Okay, so if we need to know how many electrons are in a certain constraint, we have to know what these rules are. So if I tell you that, right, if I ask how many electrons can be in n is equal to 2 and L equal to 1, we have to see, okay, what options are left over now. All right, so if we were to write the quantum number, we know that we have 2 and that we have 1. But now we're left with M sub L and we're left with N sub S. So what options can go into M sub L? What can go into that third position? Perfect, right? We can have -1, 0, or 1. And then how many options are there for each of those, right? If it's -1, how many options do we have? What's left for M sub S?
Plus one word, I mean, plus one half or minus one.
Perfect, right? So we can have plus or minus 1/2. We can do that for all of them. So how many options did we just come up with? Right, we could say we had 2, 1, -1, plus 1/2. 2, 1, -1, minus 1/2. 2, 1, 0, plus 1/2. 2, 1, 0, minus 1/2. 2, 1, 1, plus 1/2. 2, 1, 1, minus 1/2. So after our initial constraints, how many options are there? There's 6, right? So there's 6 total configurations. You could write. So how many electrons does that mean we have? Or how many electrons can be defined by n is equal to 2 and L is equal to 1? 6, right? We talked about the 6. 6 electrons can be defined, right? And those are the 6 quantum numbers that we could write from the constraints given to us. Does that make, do you see that?
Yes, yes.
Right.
Yes.
If we write this out, it would be 2, 1, -1, plus 1/2, right? That's 1 electron.
Yeah, I was just thinking, yeah, I know we had to double, I just forgot that we had already.
We had already doubled it with the plus and minus 1/2. Yep. So you could write, right, it's tedious, but you could write out all of the options just because there's only 6 of them. Right, so those are the 6 electrons we could define from there. In class today, right, we talked about the 4 electrons. You could write out the 4 quantum numbers of those electrons that are available to you. Okay, so that's one example. What if we said, how many electrons can be defined in L is equal to 3? I'll give you a couple, let's try this on your own a little bit, see if you can start working out what that might look like. Try it. Write out your quantum number constraints, what it looks like. Okay, did anyone get 18 electrons? Okay, and how did we get that, right? So if n is equal to 3, then that means that there are 3 options that L can be. L can be 2, 1, or 0. So we're saying if m sub L is equal to 2, that means, or if L is equal to 2, that means m sub L can be equal to -2, 1, 0, 1, or 2. For each one of those positions, they can have 2 electrons. So you have 10 total electrons if m sub L is equal, or if L is equal to 2. Right, do we make sense where the 10 comes from? Right, and then for L is equal to 1, we said that there were 6, right? There's 6 electrons that are there. And then if L is equal to 0, then there's only one option for n sub L that can have 2 electrons in it. So 2 come from there. So we have 18 total electrons if L is, or if n is equal to 3. Okay, do we see how that works in terms of like trying to find the constraints of what it's working in? And then we have to work with all the other options. Did everyone understand why it was 4 electrons today in class? We all saw that afterwards. Okay. Does that help with your questions there? Okay. Kind of just think of it like a puzzle and just write it out as much as possible that you can afterwards. I can kind of give you a little bit of help. Let me show you. Let me just get one that I can write on. Really blurry, but I think you understand. So if we are looking at the periodic table, right, this hydrogen starts with 1, 2, 3, 4, 5, 6, 7. We have all the periods going across. So in your first period, how many atoms do you have? How many elements do you have? We have 2, right? We have hydrogen and we have helium. And then we go to our next row, and that's where lithium starts. So if n is equal to 1, right, that's our energy level. We said that we have the options for L are equal to 0. M sub L is equal to 0. M sub S can be plus or minus 1/2. So how many electrons can we define when L is, or when n is equal to 1? 2. Where do we see those 2? In the first row of the periodic table. When n is equal to 2, how many total electrons can we have? Right, we have L can be 1 or 0. We can have -1, 0, 1, or 0. So we have 6 from this one, 2 from this one, so 8 total in the second energy level. In the second row of the periodic table, how many total elements are there? Right, we have 8 total electrons, or 8 total elements in our second row, which means we have 8 electrons that we can define from our third energy level, or from our second energy level. Do we see that way? So that also works for the rest of the periodic table. Right, so in 3, we have 2 electrons here, 6 electrons here, right? And we saw we had 10, 6, and 2. So where do we think those 10 come from? Does anyone see where there's 10 in a row? Your transition elements is a block of 10, right? And that's where your 10 electrons come for the third row. So even though they're in the fourth energy level, it's still that first time you see those 10 electrons. So that's where the 10 come from. Do you remember in class where Dr. Bengali said that the 4s and the 3d are very similar in energy level? It's right here, right? The 4s is just a little bit lower in energy. This is your 4s right here. This is your 3d right here, right? So they're very close. So the 4s fills first before that 3d. And you can see that on the periodic table because if you're going left to right, you hit the 4s before you hit the 3d. Okay, so you can use your periodic table for your advantage when you're like filling up your electron configurations and stuff. Do we know remember what the right-hand side of the periodic table was for your orbitals? What letter that was? This was P. So this is your P block, right? You have your S block, your P block, and then your D block is your transition metals. Do we see that? Okay. It's very useful if you forget. Any other questions on electrons or quantum numbers? Anything else you want to see today?
It's like
The filling up and stuff?
Yes.
Yep.
because I was doing the homework and for one of the questions, it had me fill up 3D first, and then one of the questions, it had me fill 4S first.
Okay. Do you remember what that was?
It's.
Okay.
I think the ones that are due on.
On Sunday, yep.
but I think it was one of the first, like, one of the ones that was wrong first.
Okay. I think I know what questions they're asking, but I'll look at the question first just to make sure that I'm correct with that. Okay, so when we're looking at the periodic table, right, we said we're going to fill 1s2, right? We fill the 1s first. It can have 2 electrons. We're then going to fill the 2s2 because that's what comes next, right? That's lithium and beryllium. And then we're going to jump to the 2p. So then that's 2p6. Sodium and magnesium start your third period. That's going to be your 3s2. And then you have your 3p6 as you go towards aluminum. It's then when you get to the potassium for 4s2 and then scandinavium for 3d10 where things become a little iffy. Okay. So these we said were very close in energy levels. So if we're writing the electron diagrams, anytime you have an s orbital, it's just going to be one box, right? One box or one circle, whatever you prefer. Right, and this is because m sub l is equal to 0, right? There's only one option for m sub l, the orbital. Anytime you have a p box or a p orbital, you're going to have 3 boxes, right? Because it can be -1, 0, or 1. That can each have 2 electrons, so there's 6 total electrons in there. And then for the D, how many boxes do you think we're going to have? We can have 10 electrons, 5. Yep. This is your D orbital. When we're looking at 4s and 3d10, right, what did we say about electrons? Do they like to be unpaired or paired? They like to be unpaired, right? So when it has to, it has to be up and down spin. But my teacher in high school called this the college roommate rule, right? If you could have your own room, you're gonna have your own room, right? Most people wouldn't pick to live with a roommate. So your electrons are gonna do the same thing. They would prefer to have their own room. They would prefer to have their own orbital that they're in by themselves. Only once they have to pair will they pair. They're not going to, right? They're not going to pair like that. They don't have to, they won't. So sometimes you get the case where you don't have this 3D orbital completely full, but your 4s was completely full. In this case, this paired electron pops up to this unoccupied orbital and makes this here, and we remove this here. So now we have 6 unpaired electrons instead of 5 unpaired and 2 paired. Or 4 unpaired and 2 paired. Right? Does that make sense? Do we see that? It's because these are so close in energy that we're able to jump that up, and it actually lowers the energy of the electron. So I think that's happening in your homework questions, where they now have the opportunity to have a lower energy, right? If you can be lying down, you're going to be lying down. The electron wants to be lying down as well, or the atom wants to be lying down. So it's going to do what it has to in order to lie down. So it's going to pop its energy or its electron up to a higher energy level, which ultimately relaxes it all the way. The other time this happens is, oops, right? We have a paired in the 4s, and we have your 3D almost completely paired, but there's one missing. It is actually energy favorable for the atom to take that paired electron in the 4s, bump it up here to pair in the 3D, because that actually lowers its energy as well. And so therefore we have 1 4s1 3d10, and this becomes 4s1 3d5. Do we see what's happening there? Does that make sense? So this only occurs in those columns on the periodic table. So the first instance of that is chromium. Chromium, if you were to write this like electron configuration, is argon, right, for doing noble gases, 4s2 3d4. It doesn't actually exist as 4s2 3d4. It's actually 4s1 3d5. Okay, and the other one is copper. Copper is argon 4s2 3d9, but it's actually argon 4s1 3d10. That makes sense. So under chromium is molybdenum, right? It would also do that. And cadmium, oh no, sorry. And silver is under copper, right? It would also do that. Other than that, like those other ones, you don't really need to worry about. Anything past the 5th period, you don't really need to worry about. If that doesn't help your homework, let me know and I can try and explain it.
No, that's,
Okay.
that makes sense. So you're talking about like one, if it wants to lie down, then
Yeah.
it will, and then you're trying to make it as stable as possible.
Yep.
And so by bumping it up and then.
Yep. I always think of this as like what I would be doing. So if it's 4S2 3D10, I'm like lying down but sitting up. But if it's 4S1 3D5, then I'm like horizontal, right? Right. I'm still lying down, but I could be almost horizontal, right? And then the same thing for 4S2 3D9 or 4S1 3D10, right? Lying down but sitting up or just completely lying down. Any other questions? I relate myself to an electron all the time. I'm like, what gets me in the lowest energy state? And I just think about that. Anything else we have questions, concerns on? Do we like this stuff? I think quantum numbers are kind of fun. They're like a puzzle, so if you think of it like a puzzle, maybe you'll have more fun with it. Yeah, thank you. Other than that, I think the only thing that might show up in your quiz for Monday is the de Broglie wavelength. So when we talk about that, that's different than your regular wavelength. This now becomes velocity. Right, it's not, doesn't have a little tail, it's not frequency, and this is mass. And this is mass in kilograms. So you just want to make sure that that is the same. H is still the 6.626 times 10 to the negative 34, but it's in joules per mole joules times seconds. So that's why your mass has to be in kilograms, because joules is defined by kilograms. And velocity is in meters over second. So if you see a question like that, just make sure all of your units are correct before you solve it. Yeah. Yeah, lots of waves for quiz Monday. And then electron configurations and quantum numbers, I would say, are the big boys. I'm just gonna look ahead at the rest of it. Yeah, and then you talk about ions a little bit on Friday and whatnot, but hopefully that makes sense. Should come down to the energy levels again and it'll make sense. Anything else?
Can you just repeat what you said in the three big ones? for the
Yep,
quiz?
so anything waves, so, right, energy is equal to H times frequency, and then C is equal to lambda times frequency. Those equations are big, and then, right, you can combine those to say energy is equal to HC over lambda. I would definitely know your electromagnetic spectrum. Just, you don't need to know like values for them necessarily, maybe the visible spectrum, just like the general range, but know which one's your highest energy, which one's your lowest energy kind of thing. And then your quantum numbers is your other one of the other threes, and then electron configurations, right? So being able to say, okay, I have magnesium, what's the electron configuration for magnesium, kind of thing. Yep. You'll talk about electron configurations of ions But if you understand like this building up of the orbital diagrams, then the electron configurations for ions will make sense. Because it's just plus or minus an electron, so then that's just adding an arrow or not. Yep. Okay, if there's anything else, let me know. I'll stick around for a little bit if you have questions, but if we're done, it can be done. That's okay. Yeah, thanks so much.